Hello and welcome to the first part of the lesson on optimization. Now, optimization is something that you have done in the past. You first encountered optimization problems in grade 9, and then there were also some optimization questions that you should have seen in grade 10 and 11 to do with quadratic relations. But one of the most important applications of derivatives occurs in the solution of optimization problems, in which a quantity must be maximized or minimized. Now, there's a strategy for solving optimization problems. The first thing is to recognize the type of problem. You want to look for words like greatest, most, fewest, least, maximum, minimum, largest, smallest, etc. The word best or optimal could also be used. It could mean biggest if talking about profit, for example, or smallest if talking about costs. You also want to identify the variable that is being maximized or minimized. Then what you want to do is you want to establish a formula. This may be a formula that you are expected to know, such as the area of a circle, Pythagorean theorem, etc., or it may be provided as part of the problem, or you may be able to develop it using information given in the problem. It is often helpful to draw a diagram. So these are some common formulas that you have encountered in the past. So the formulas for the area of a circle, the circumference of a circle, the volume of a sphere, the surface area of a sphere, the volume of a cylinder, the surface area of a cylinder, volume of a rectangular solid, surface area of a rectangular solid, the perimeter of a rectangle, the area of a rectangle, and then lastly the volume of a cone and the surface area of a cone. So these are all formulas that you have seen throughout the years. Now, after you have figured out what formula you're going to use, you then prepare for differentiation, for taking the derivative. So before you differentiate, it is imperative that you eliminate any extra variables from the formula. There can only be two variables remaining, the one that you are attempting to optimize and one other. It is also a good idea to put the formula in a form that will make the process of differentiation as easy as possible. To eliminate extra variables, you can use substitution. So substitute using relationships that are provided in the problem, such as, for example, the height might equal 3 times the radius, or relationships that are common knowledge, such as the fact that the diameter is equal to 2 times the radius. If any variable remains constant in this problem, you should substitute the value at this point. So let's say we have pi, right? Pi is a constant value, or we just have a value for a variable that we know what it's equal to and it's not changing. So you must substitute values which are not constant. Then lastly, these are the last 4 steps. So you would take the derivative. So you differentiate the variable to be optimized with respect to the second variable kept in the problem. You would use appropriate rules such as the product rule, quotient rule, chain rule, implicit differentiation, etc. It is probably best to use this form, the Leibniz notation. So like, for example, dv by dr, if we're taking the derivative of a volume function with respect to radius. Then after finding the derivative, you would want to find maximum or minimum points. So you let the derivative equal 0 and you find sign change points in the usual way. You test these values to determine which is a maximum and which is a minimum. You use the first derivative sign line to do this. For most problems, it will be obvious which is which, but you should do the test for sake of form and completeness. And then lastly, since these are word problems, you would want to answer them with a therefore statement. So you would check the problem to see what information is requested. It could be the actual maximum or minimum value, or the value for the second variable at which the maximum or minimum occurs. It could be both. Make sure you make a formal statement of the answer. Now we're going to take a look at some examples of optimization problems. So this first problem involves fencing. So farmer plans to fence in a rectangular field next to a river. The side of the field along the riverbank does not require fencing. The two sides of the field that are perpendicular to the river must be made with a rust-resistant fencing material, which costs $9 per meter. And so when trying to solve a problem like this, you would begin by drawing a diagram. So we have, first off, what I can do is I can draw the river. So let's say there's a river, and then there's fencing. That needs to be constructed in the form of a rectangle. Now I'm going to assign variables to this. I'm going to say that this is going to be y, and this is going to be x. So this is also y here. So the length of fence parallel to the river can be made with a standard fencing material product, which costs $7 per meter. The field must have a total area of 400 square meters, and each dimension of the field must be at least 10 meters in length. So we're given a restriction. What dimensions will minimize the cost of building the fence? Okay, so I'm going to start by developing an equation. And so in this case, we are given the area, right? So the area is equal to x times y in this case, and we know that it is 400 square meters. Now I'm going to need another equation as well, so I'm going to use the information in the question that the fencing that is perpendicular to the river costs $9 per meter, and the fencing that is parallel to the river costs $7 per meter. And so I'm going to create a cost function where there are two parts to the fence that are perpendicular to the river. So I have this 2y part. Now this 2y is being multiplied by $9. And then there's just one part labeled x, and for that it costs $7 per meter. So that's going to be 7 times x. And so this ends up becoming 18y plus 7x. That's my cost function. And I'm going to be working with the cost function because I'm trying to minimize the cost of building the fence. Now what I'm going to need to do is I'm going to isolate for one of the variables in my area function. And so my area function, so I'm going to decide to substitute, I'm going to isolate for y. So y is equal to 400 over x. And now I'm going to substitute that into my cost function. So cost is now going to equal 18 times 400 over x plus 7x, multiplying that out, 18 times 400 is 7200 over x plus 7x. So this is in terms of x. So c of x. Now the next step is to find the derivative so that I can find the minimum or maximum. Now in this case, I'm looking for the minimum. So I'm going to differentiate my function that now contains only one variable. So it's all in terms of x. And so this is going to become negative 7,200 over x squared plus 7. Now I'm going to set the derivative equal to 0. So the negative 7,200 over x squared plus 7, I'm going to set equal to 0. And so solving this, I'm going to have negative 7,200 is equal to negative 7x squared. Now I'm going to divide 7,200 by 7. That doesn't work. That doesn't give me a whole number. So instead, I'll have 7,200 over 7. I'm going to have to take the square root of it to get x. So 7,200 divided by 7, square root of that answer. So x is 32.07 meters. Now that's within the domain because it says each dimension of the river must be at least 10 meters in length. So now what I'm going to do next is I'm going to find what y is. So I'm going to use this equation here. So y is equal to 400 over x. I'm going to substitute x in. I'm going to divide by 32.07. So 400 divided by 32.07. I'm going to get 12.47 meters. And now what I can do is I can check to make sure that this truly is a minimum. And so I'm going to use a number line. My critical value here is what I found, the 32.07. And then at one end, actually, here I have I have 10 because I can't go below 10. So 32.07, and then the other end, there isn't really a restriction on x. So technically it can be very large, it can be very extremely large. So I'm going to take my derivative function and now I'm going to check the signs. So I'm going to start by substituting something less than, actually this should be 10, not 0. So something between 10 and 32.07, I'm going to use 20. So substituting 20 in here, I'm going to get negative 7,200 over 400. That's a negative number, plus 7. So let's see what that's going to be. Okay, so that's going to be negative 18. So that's going to be a negative. And then if x is larger than 32.07, let's see what happens now. So I'm going to use 35 as my test value. And now I'm going to get a positive, which tells me that this cost function is first decreasing and then increasing. So I definitely have a local minimum. So the last thing you would want to do is you would want to write a therefore statement. So the dimensions would be, so the fence with a minimum cost would be 32.07 meters by 12.47 meters. Okay. Now you could elaborate on this and also talk about the length of the fencing that would cost $9 and the length of the fencing that will cost $7. So that could also be added to your final statement. Okay, let's take a look at another optimization problem, a different type now. So this one deals with a box with a square base. So if 2,700 square centimeters of material is available to make a box with a square base and an open top, find the dimensions, so the length, width, and height of the box, that give the largest volume of the box. What is the maximum volume of the box? Okay, so first thing you would want to do is you would want to draw a diagram. So all these problems, it's a good idea to try to draw a diagram. So we have a box with an open top. And it's a square base, so it has the same base. So I'm going to let x be the length and width of the box, and then h is going to be the height of the box. And we are trying to determine what the maximum volume of the box is. So the formula for volume in this case would be x squared, so length times width times h times the height. Now I'm also going to write a formula for the surface area of the box because we're given how much material we have here. So the surface area would be the bottom, so that's x squared, right? Length times width, plus 4 times the sides, so 4 times x times h, and then there's no top. So that would be the formula for the surface area. Now we know that the surface area is 2,700. So 2700 is equal to x squared plus 4xh. And now what I'm going to do is I'm going to isolate for h in the surface area formula in order to replace the h in the volume formula with what it is in terms of x. So 2700 minus x squared divided by 4x is going to equal h. And so the volume in terms of x is going to be x squared times 2700 minus x squared over 4x. Now I can simplify this a bit, cancel the x's. So I'm going to cancel the x in the denominator. I'm going to have x times 2700 minus x squared over 4. And now I can simplify this a bit more. So 2700 divided by 4 is going to be 675x minus x cubed over 4. So that's 1 over 4 x cubed. So 1 over 4. And not surprisingly, this is a cubic function. Now the next step is to find the derivative, and then after that set it equal to 0. So differentiating this cubic, I'm going to get 675 minus 3 over 4 x squared. Now I'm going to set it equal to 0. I'm going to move the 3 over 4 x squared to the other side. And so I'm going to multiply 675 by 4. Then I'm going to divide by 3. I'm going to get 900. So x squared is equal to 900. Then taking the square root of this, the square root of 900 is 30. I'm going to ignore the negative because it doesn't make sense to have a negative base length. And then this is in centimeters. So now what I'm going to do is I'm going to find the height as well. So in order to find the height, I'm just going to use this equation here. So the height is equal to 2700 minus 30 squared over 4 times 30. So 2700 minus 900 divided by 120 is 15. So 15 centimeters. Now I need to confirm that this truly is a maximum. So I'm going to use the second derivative test. I'm going to find the second derivative first. So v double prime of x is equal to negative 9 over 4 x. Now it's apparent that this function is negative if x is positive. So f double prime at 30 is going to be less than 0. So therefore, there is a maximum at x is equal to 30. And then the last thing is just to write a therefore statement. So we would just write the dimensions of the box. So the box with the largest volume will be 30 centimeters by 30 centimeters by 15 centimeters. Okay, let's now look at another example, one more example. So a cylindrical tin can is to be made with 500 square centimeters of tin. Find the maximum possible volume of the can. Now this question is somewhat similar to the previous example, except we're dealing with a cylinder this time, not a box. And so we have a cylinder. Now it's not really essential to draw the cylinder here. It's not really going to help us that much. But what you can do is you could start by writing the formula for the volume of a cylinder. And that's pi r squared h. So the area of the circular base times the height. And then the surface area of a cylinder is 2 pi r squared. So that's the top and bottom circles, plus 2 pi rh. So that's the circumference of the top or bottom circle times the height to get the lateral portion of the cylinder. Now the surface area is 500. So 500 equals 2 pi r squared plus 2 pi rh. And now, just like similar to the previous example, I'm going to isolate for h so that I can substitute that into the volume formula. So I'm going to have 500 minus 2 pi r squared over 2 pi r is equal to h. And I'm going to replace now in the volume formula. So v of x is going to equal pi r squared times 500 minus 2 pi r squared over 2 pi r. And I'm going to cancel the pi's and the r, leaving me with r times 500 minus 2 pi r squared over 2, just over 2, yeah. Yeah, so these pi's cancel out. This r cancels out and the 2 cancels out here. Now, simplifying this further, I'm going to have 250 r minus pi r cubed. So yeah, the 2's will cancel out there. Now I'm going to find the derivative. So I'm going to end up with 250 minus 3 pi r squared. And now I'm going to take the derivative and set it equal to 0. So I'm going to get 0 equals 250 minus 3 pi r squared. So 3 pi r squared is equal to 250. Then dividing that by 3 pi and then taking the square root, r is going to equal, so 250 divided by 2 pi. And then the square root of that is going to be 6.31 centimeters. Now what I'm going to need to do is I'm going to have to find, now that I have the radius, I'm now going to have to find what the maximum volume actually is going to be. So to find the maximum volume, I'm going to also have to find what the height is. So in order to find the height, I'm going to use this equation here. So 500 minus 2 pi times 6.31 squared over 2 pi times 6.31. That's going to give me the height of the tin can. So 500 minus 2 pi times 6.31 squared divided by 2 pi times 6.31. Okay, so that's also going to be 6.3, interestingly. So 6.3 centimeters. And so now finding the volume. So pi times 6.31 squared times the height, which is 6.3. I'm going to end up with 788 cubic centimeters. Okay, so notice how this question is not asking for the dimensions, it's asking for the maximum volume. So therefore, the maximum volume of the tin can would be 788 cubic centimeters. Okay, so the only other thing you could do here is you could confirm that this truly is a maximum. So if we find the second derivative of the volume function, it's negative 6 pi r, and at 6.31 the second derivative is less than 0. So therefore there's a max. Is a max at x is equal to 6.31. So that's just a check, a formal check. Okay, so that brings us to the end of this lesson. Thank you for watching, and make sure that you practice doing optimization questions. The key to becoming good at solving these types of problems is to do a lot of practice, and you would want to become comfortable with different types of questions. So the more questions you see and you attempt to do, the better you will become at solving optimization problems. Okay, well, thank you for watching, and until next time.